Hello Year 12. I hope you had a really good Easter break. I'm starting back again with some videos to help you get through the last bit of the Year 12 course. This is the last chapter that we need to cover, which is on exponentials and logarithms. The first lesson is looking at the exponential curve, which is something I think you've probably seen way too much of in the last few months and weeks. We're going to look at its graph and we're going to look at some of its properties. Okay, so I've opened up Desmos. I've set up an exponential graph, which is looks like this: y equals a to the x. A is my base. Currently, a is 2, so this is y equals 2 to the x. And we should all be hopefully already familiar with the shape of the graph. It grows quicker and quicker the more we go up to the right, and then it decays and approaches the x-axis on this side. Okay. If I increase the base, it's going to grow faster on the right hand side, and it's also, if you look at the left hand portion as well, it's going to hug the x-axis tighter. So increase the base, look, grows faster on the right, and it goes towards the x-axis a bit quicker on the left as well. Okay, so I can change all of that. Now if I decrease and I get towards 1 for my base, you can imagine what happens there. If I put 1 to the x, that's going to be a constant function, okay? Because 1 to the anything is just 1. That's a special case. If you decrease further, so that's going back towards 1 again, and then going into numbers between 0 and 1, you've got exponential decay, okay? So exponential growth looks like that. Exponential decay looks like that, okay? If I put in my base to be 0, I've done that already, then you get this purple line over here, okay? 0 to the anything is 0. And you might wonder why it's only got the right-hand side of this function, okay, only positive values of x. Well, you might want to think about that. What would happen if you plugged in a negative number into this second function here? If it was 0 to the x and you put in -1, what would happen? Okay, why can't you graph that? Okay, so that's basically the shape of the exponential curve. There's one other thing I can show you as well. If I put my a back to 2, and then I make b a special value that relates to it, if I make it 0.5, okay, so you'll notice that these are mirror images, okay, of each other. Okay, it's a reflection in the y-axis, and you'll probably know why that is. That's because of the relationship between 2 and 0.5, in that they're reciprocals. Okay, this is 2 to the x. Okay, if I think of 0.5 as being a half, then using index laws, I can show how it links to this. So I'm going to put the x on the bottom of the fraction. And then this fraction over here is the same as 2 to the minus x. Okay, so that's an alternate form for this function over here. So what I'm saying is if you take reciprocals of your base, then you're going to move from exponential growth to exponential decay, or vice versa, okay? And the result on the picture is that these graphs will be mirror images, okay? So that's how the graphs are plotted and how they look. Last piece of information you should know as well, all of these graphs will go through this point over here, 0, 1, okay? And that's because whatever the base, okay, and we're always going to be taking positive values for a, okay? You might want to think about what happens if you make a be a negative number. But if a is positive and you raise it to 0, then that's always going to be 1. So that's why you always go through this point down here, 0, 1. All right. Finally, the way that we describe the equation of the exponential curve is quite important. So rather than just the base and the power as x, you might see another constant in front as well. Okay, this is a more generalized idea of an exponential function, okay, with 2 parameters rather than 1. And if you know 2 points, you need 2 separate points to work out what these parameters p and q are. Okay. Oh, and remember as well that with BIDMAS, the x is only applied to the q, p is multiplied in front separately. Okay, so let's look at this picture. This is pq to the x. I know 2 separate points. These are x and y values. If I plug them in, I can work out p and q, these parameters. So I'm going to write out what points I've got. I've got 0, 5. They can go into my function, so y is 5, and then that's equal to p times q to the power of x, which is 0. Q to the 0 makes a 1. So p is 5. That's the first point covered. The second point is 245. I can use the information in the previous line as well, but let's plug them in first of all. So 45 is y, and that goes there. P I'm going to replace in a second, but q is now to the raised to the power of 2. Let's replace our value of p, because we know it's 5. Okay, divide by 5. Okay, so 9 is q squared. I can take square roots. You might wonder about two possible answers when you take this square root, but we're only ever going to be taking positive values of q, as I mentioned before, positive bases, so it's only positive 3. Okay, so p is 5, q is 3. Now I know that, I can rewrite my expression for my function. So in fact, y equals p is 5, and then it's, I'm going to put brackets to separate it, and then it's 3 to the x. Okay, and then when x is 3, you can work out y. Okay, 3 to the power of 3 is 27, and 5 27s is 135. Okay, so you can substitute in values. What you might notice about these two parameters is that just like when you've got a linear function, which I might write underneath actually, these two numbers relate quite nicely to the two parameters that you have for a linear function. Okay, in the linear case, the m tells you something about the rate of change. Okay, it tells you the slope of the graph, the gradient, and c tells us something about what happens on the y-axis. Okay, at the initial moment of the graph when x is 0. Well, it's quite similar for exponential. Okay, so p. Just like with my example, you notice that that told us the y-intercept. Okay, it's the same for an exponential. So that p is the y-intercept. Okay, when you get x to be 0, that's what you get. And q, well, similarly to the value of m, it's the rate of change. Okay, it tells you about how quickly this graph grows. Okay, so I'm going to write it as the rate of growth. Okay, so whenever your x increases by 1, if I take one step to the right, then the effect on the graph is going to multiply the function by q. Okay, so it's like a multiplier that gets you from each x value to the next. Okay, and that's exponential graphs pretty much covered. So good luck with the questions. I hope you settle back into the next term of the year well, and I'll hopefully see you soon. Bye now.